at the end of class yesterday, Mr. Dickey went over, okay, the solution to this with you, okay? And what we should have discovered is that the centripetal acceleration on this big corner was significantly less than the centripetal acceleration for the small corner, okay? I mean, kind of common sense or life experience would tell you that. If you take a, if you ever watch like somebody racing, they almost always try to go as close to the inside of the corner as possible, but then they go out wide. In fact, in racing, what they usually do is start out on the outside, and then they come close to the inside, and then go back out to the outside. By doing that, what have they done to the radius of the corner? They've increased it. They've made it bigger, okay? They're not taking this corner, okay, with this radius. They are taking, okay, a much bigger corner by simply going from inside to outside with a much greater radius. Okay? That way they can take the corner faster. Sort of make sense? Okay? That's what they do by taking a corner like that. I am not telling you how to speed or drive like a racer. That is not the point of this demonstration. Okay? But that is how a race car driver would take a corner. So obviously radius affects the amount of centripetal acceleration and the amount of centripetal force. So taking this corner wider like this means you could take it faster. Everyone all right with that idea? Okay, now when we did that calculation, when you guys did that calculation, the radius was 3 times greater here than it was here. Was the centripetal acceleration 1/3 in this corner of what it was in the other? It was. Okay, so they have an inversely proportional relationship. Okay, as radius increases, there will be a linear decrease in the amount of centripetal acceleration. So I make the radius 3 times bigger, the centripetal acceleration will be 3 times smaller. All right? Everybody all right with that idea? Okay, so radius is only one of the things that affects centripetal acceleration. Speed is another. Okay, and we talked about this yesterday. Because speed is squared in that formula, it has a greater effect on the centripetal acceleration. Okay? Because it's squared, that relationship will now be exponential. So if I double my speed, I will need 4 times, or that will produce 4 times greater centripetal acceleration. If I triple my speed, 9 times greater centripetal acceleration. That's what you need to keep in mind when you take that corner out there, okay, when it's icy. All right? Going 2 times faster than, well, a well-advised person would go, okay, is going to result in you or your car, or both, taking a cold bath in dirty water, okay, because that's what's in the pond. Still go in there, okay. So that's what would happen. So what we're going to look at now is what happens if we keep the radius the same, but now we change the speed. Okay, so, sorry, let's go back to this here, because I thought I had that example there. Let's say that we're just going to deal with the 320 meter corner, all right? But we're going to go from 28 meters per second, we're going to look at 28, and we're going to look at 14 meters per second, all right? So if I take the 320 meter corner, okay, at 14 meters per second, so I'm going to have 14 squared on the top, divided by 320. Okay, I'm going to get a certain number for my centripetal acceleration. Okay, and then the second situation will be same corner, but now I'm going to go at double that speed, 28 squared over 320. Okay, so we got our 14 squared, okay, divided by 320. All right, so the centripetal acceleration is going to be 0.6125 meters per second squared. Okay, but if I double the speed, I didn't double the centripetal acceleration. quadrupled it. Okay, that's that whole exponential relationship thing that we've gone over a number of times in this class. Okay, if I double my speed, there is going to be much greater centripetal acceleration produced. What that's going to feel like for people inside the car is, okay, at 14 meters per second, they're going to be slightly pushed, okay, or feel slightly pushed towards the outside of the car. It's actually that they're not pushed, their inertia just wants them to go straight, and they get their face planted against the window and they're grabbing onto the holy crap bar for dear life. Okay, well, if you take that corner at 28 squared, they're going to feel a quarter of their weight now pushing against the windshield or pushing against the window, okay, and they're barely going to be able to hold on to the holy crap bar, and they're going to be very upset with you as the car flips over because you're going too fast. Okay, it's a very different situation if you're taking that at double the speed that you should. Okay, everybody all right with that? Okay. All right, now yesterday I mentioned the whole David and Goliath thing, so I'm going to show you the video, okay, on that. And so we can get an idea. Okay, so just using that same technique, right? You got the rock here where my thumb is, okay? And they just kind of do this to make sure that they get it going fast enough. Then they can put it over their head, make it go really fast. They let go of the knot, okay? And the rock flies out, okay? As long as they release it at that point, okay, where it's a tangent to the circle and it's going to encounter the target, okay, then they can hit the target, all right? And with more force than was necessary. Okay, the doctor said 3.2 kilonewtons. When he hit the target, it was 3.6. Okay, so more than enough, okay, to, well, make the stone sink into his forehead as is described in the Bible. Okay, so if that's a skull fracture, it's a massive hemorrhage in the brain, okay, and it's fatal. Right? Now, I guess the lesson for warfare here would be, if you have the superior army, don't make deals. Okay? Like, you knew you were going to win, but rather than kill everybody, but okay, the sentiment is good. Okay, like Goliath was actually being kind in that case, where he was like, hey, look, we don't have to kill you all brutally with swords and stuff, you know, and you can just, you know, kind of capitulate. I won't kill you all, and then let a boy brain you with a rock. You know, maybe you don't make deals when you have the superior military force. Now, the worst part of that is the part that most people don't talk about. It's what David did after. Anybody know what David did after?
Did he dance?
No, he cut off Goliath's head, took it back and showed it to his family, Goliath's family, and then killed them. Okay, yeah, David was not a nice guy. Okay, he kind of got drunk with power real fast, okay, after becoming king. Our Savior's a direct descendant of him. That's that. You remember that? Sometimes they read that gospel reading where it's like so and so beget so and so beget so and so. It goes on for like 5 minutes of who was whose father. Okay, that's to trace the lineage from David to Jesus. Okay, proving that he would have royal blood and be able to be the king of Egypt or king of Israel. Sorry. So yeah, he's related to him. But King David was not nice. He did a lot of like really awful things as king that we don't generally talk about, but they're all in the Bible. Okay, all the awful stuff that he did is in there. So anyway, it got the Israelites from being this minor kind of puny nation that nobody respected to a reasonable power at the time, until of course the Romans came along, okay, and kind of put an end to all of that. All right, so that's, okay, centripetal force, centripetal acceleration. It's the tension in that sling that's acting as a centripetal force. When that thing is whirling around and around in the circle, okay, the sling, the inertia of the rock pushes against the sling, and the sling, according to Newton's third law, pushes back. Okay, and that acts as the centripetal force. It ends up being the tension in the sling, okay, that's holding the rock in the circle until you release that knot and the rock flies off. Okay, so talked about that. Okay, let's move on to centripetal force then. We got the centripetal acceleration stuff out of the way. Okay, let's talk about centripetal force. Okay, so this is lesson 2 now. Centripetal acceleration relates directly to centripetal force because of Newton's second law. Okay? Centripetal acceleration is v squared over r. Newton's second law says that force is mass times acceleration. Right? And we saw that like the force of gravity was mass times the acceleration due to gravity. Okay, we said that basically any force could be calculated if you knew the acceleration it could produce and the mass it was acting on. Okay? So the same is true for centripetal force. Okay? Centripetal force is mass times centripetal acceleration, which means it's m times v squared over r. That will be your fundamental formula for this unit. It is Newton's second law applied to circles. Okay, so mv squared over r, you will use that like you used m times a in unit 2, because it is m times a. So do the same things then affect centripetal force as affected centripetal acceleration? And in the same way. You increase the radius, you will linearly decrease the centripetal force. You increase the speed, you will exponentially increase the centripetal force. Okay? The only thing that's new is mass. Okay? If you increase mass, you will linearly or proportionally increase the centripetal force. Okay? I mean, think about it. If I'm, doing this, whirling this tape around in a circle, I don't have to hold on to the string very hard. Okay? But if I put a 5-pound sledgehammer on the end of this string, okay, am I going to have to pull a little harder? Yeah, because I've got more mass. Even if I'm swinging it at the same speed, I'm going to have to hold on a lot tighter because there's just way more mass and thus more inertia to leave the circle. I have to pull harder to keep that mass in. All right? Everybody okay with that? It's kind of how hammer throw works, if anyone's ever seen the hammer throw. Okay, in track and field, okay, there's like this big ball on a chain, okay, and you hold on to one end and you spin around really, really quick and you get that thing going and then you just let it go, okay, and it flies out into the field. That's exactly the same idea, okay? You hold on to that thing and the faster you can spin, the further that hammer will go. Okay, so all of it comes down to how strong is that person and how fast can they spin around without getting dizzy, falling over, and losing control of the hammer, which happens sometimes. Okay, I've seen it. Okay? It goes into the cage, okay, or goes backwards, or they just fall down and it almost hits them. Okay? It can be pretty dangerous because it is, after all, it's basically like a big heavy shot put on a chain. Okay? It's a lot of weight that you're winging around in a circle really fast. All right, so centripetal forces operate this way. They push or pull. And they push or pull which way? If they're centripetal, they point always in, towards the center of the circle. So that's what centripetal means. Okay? If something is centripetal whatever, it's towards the center of the circle. Okay? All right, so we're going to talk about 2 different kinds of corners today, okay, that operate similarly, but in different ways. They try to keep an object moving in a circle, okay, but they use different forces to keep it that way. All right, so we're going to talk about banked curves as well as unbanked curves. So unbanked curves would be, you take a turn here in town, the road is flat. A banked curve would be like the on-ramp out here, okay, it's tilted, right? So when you go around it, okay, you've got a little bit of extra force pushing you back towards the center because it's not flat. Okay, so we'll talk about how both of those work. All right, so Newton's second law, this is what I demonstrated to you before, okay, says that mass times acceleration is net force. Okay, for something to move around and around in a circle, it has to be accelerating towards the center, which means there has to be a force, a net force, pushing towards the center. So the vector sum of all the forces acting on that object add up to towards the middle. Okay? If that wasn't the case, then the object wouldn't move in a perfect circle. All right, and so that is where, okay, the formula we just talked about comes from. Centripetal force is mv squared over r. Now, this is where it becomes a bit like what we did in the last unit. Okay, we know that net force is the vector sum of all forces. Okay, Okay? The same is still true for an object moving around and around in a circle. And when we get to vertical circular motion, you'll see kind of how that applies. Okay? Fc, centripetal force, basically means the force is acting in minus force is acting out. Okay? That would get us our net force in. Now, for the first bit of this unit, there won't be any forces acting out. That only really comes in when we start talking about the vertical circular motion. Okay? But for uniform circular motion, there's just going to be the inertia of the object trying to go in a straight line and the centripetal force preventing it. Okay. All right, any questions on that part there? All right, so lots of things can act as a centripetal force. Gravity is what holds the moon in orbit. Gravity is what holds the Earth in orbit around the sun, and our sun in orbit around the main giant singularity that exists at the center of the Milky Way galaxy, and so on. Okay, gravity acts as a centripetal force. Okay, friction can act as a centripetal force. Tension can act as a centripetal force. Magnetism, electricity, all of those, okay, will produce centripetal forces. All right, it's generally how old CRT TVs would work. Okay, how many people have seen one of those old tube TVs? Okay, those worked using magnetic fields and causing basically particles to curve so that they would hit other parts of the screen, producing the image on the screen. By comparison, an LED TV, which is what we use in kind of modern times, is actually quite a bit simpler. Okay? Not having to have like a gun that shoots electrons in the back of the TV and a giant glass tube to throw them at. Okay? That was basically how it worked. Now you just light up the LEDs. All you need is a computer to tell which LEDs to light up and what color to be. Okay? So that works quite a bit easier. This plane here, obviously the centripetal force is being provided by the string that's connected to it that the person is using to whirl it around and around. Okay? We're actually going to do a lab on that after Easter, okay, where we're going to have a rubber stopper on a string, and we're going to have a piece of PVC pipe. The string will run through the pipe, so you can't hold the string. Okay? We're just going to put a mass underneath that tube connected to the string, and only that mass will act as the centripetal force to hold the thing in motion. It's going to be fun because I'll get to watch you guys like bump your head with the rubber stoppers a little bit, okay? Because it happens. Okay? You can wear protective glasses so no one gets a shiner, okay? Because that's actually happened once too. All right? But it's just the rubber stopper going to be moving around the circle, okay? And the weight of that mass is what's going to hold it in the circle. Okay? And what we're going to see is what happens to how fast that rubber stopper goes as we increase the weight that's underneath the tube. Okay, more weight means more tension in the string. Should mean then that we should be able to make the rubber stopper go faster or slower? Faster. Increasing weight means more centripetal force, which means more speed, okay, for that object. Okay, so let's say here we're going to look at the effective speed on centripetal force. All right, so we know centripetal force is mv squared over r. Okay, we know the mass of this plane, 0.90 kilograms, and it's moving at a constant speed. What we want to find is the centripetal force, the tension, okay, for speeds of 19 and 38 meters per second on a 17-meter long line. So we have mass, we have radius, okay, and we're going to see what Fc is for two different speeds. All right, so the centripetal force for the 19 kilogram. Okay, that's going to be 0.9 kilograms times 19 squared divided by 17 meters. All right, so that's going to require 19.1 newtons of tension, centripetal force, to keep the plane moving around and around, okay, at 19 meters per second. Now, if I put that up from 19 to 38, is 38 double 19? It is. Okay, so now if I say, what's the centripetal force at 38, okay, 0.9, same plane, times 38 squared, divided by same string, 17 meters. Okay, pretty sure. Yeah, that's 4 times greater. Okay, so it is an exponential relationship. I doubled the speed, but I'm gonna need 4 times as much centripetal force to hold that in. Okay, and that's pretty obvious. If you whirl something around and around in a circle and the speed is nice and slow, okay, I don't have to hold on to that string very tightly. Now I'm holding on to it really tight because I don't want anyone to get hit by this thing. Okay, so yeah, the faster it goes, yes, definitely, the harder I would have to hold on to it. Okay, and it was a lot faster, and I had to hold on to this a lot harder. It really wanted to go places. Okay, where would that place be? If I accidentally let it go, it would travel straight, tangent to the circle, wherever it leads. Okay, everybody good with that relationship? Okay. Okay, so the effective radius, is that going to be the same as what we found yesterday? If I make the radius bigger, the centripetal force will get smaller, because I'll be dividing by a bigger number. Okay, R is bigger, okay, FC will get smaller, and it's going to be inverse but linear. Okay, so if I double the radius, I will need half as much centripetal force. Okay, and that would also be pretty obvious. Okay, if I only use half of this string, okay, at this speed, I got to hold on to it pretty tight. Okay, but if I use the whole length, okay, at that same speed, okay, I don't have to hold on to it very hard at all. Okay, it's about the same speed, but I'm not holding on to it very tight because I just increased the radius. Okay, take the corner wider or take the corner slower, and you're not going to end up in the pond. Well, don't take it too wide, because then you might end up in the pond anyway. Okay, but we definitely want to take it at one of those 2 options. All right, so this was just doing kind of the same thing. Okay, if we did that for an 11-meter radius, it required 64 newtons. Okay, but if we used a 22-meter radius, okay, it required half as much. I doubled the radius. I needed half as much force. Come on. Okay, so if we take a corner at a high rate of speed, so you're in your car with your crazy driving friend, okay, and they go around the corner, what holds you in the car? Seatbelt. Hopefully you're wearing that. Okay, that'll be the first thing. Okay, you try to go outside the car, and the lap belt is going to hold you in place. The shoulder belt, not as much. Okay, the shoulder belt is more about going forwards. Okay, so the lap belt is going to keep you from moving laterally, right? But your upper body is quite far above the lap belt, so your upper body is going to tilt, and it's going to hit what? Door. The door. Hopefully you're driving a car with doors. Okay, if you own a Jeep that you can take the doors off, don't take the doors off. Okay, I was once your age. I know that seems like a long time. We had cars then. Okay, we had Jeeps that didn't have doors, and I had a buddy who took a corner really fast. Another friend of mine was in the passenger seat, not wearing a seatbelt. Whoop! Out the door he went, straight line. I wish we had camera phones then, okay? Because that would have got 1 million hits on YouTube for sure, okay? Because he went out, as he was going around the corner, he reached for the bar and he missed it, okay? He reached for the holy crap bar, okay, there on the A-pillar, and he missed it, and out the door he went, and he rolled, okay, along the parking lot. He was pretty scraped up, okay, in a nice straight line, okay? Nice straight line, okay? But it was totally what you would predict would happen. All right, so if you have a Jeep and you take the doors off, make sure you're wearing your seatbelt, okay? Because that's really unsafe to not have doors. They're really part of the whole safety and collision system of your car, okay? But that's what would happen, okay? If you have the doors on, you hit the door, okay? Your inertia is what's making you try to leave the car. That's what we mistakenly call centrifugal force, okay? We feel like there's this force pulling us out. Well, it's not trying to pull you directly out. It's just your inertia wanting you to go straight. But that inertia causes you to push on something that's going to push directly back. So we feel a force that feels like straight out, but it's actually straight back in. Okay? It's the normal force of the door. When I hit the door has to push back. and it pushes back towards the middle, okay? After Easter, we'll actually talk about how artificial gravity is produced. If you've seen The Martian or any kind of modern science fiction movies, there's always part of the ship that spins, okay? That works on the same concept. You're standing inside a spinning drum, okay? And you want to go straight, but the floor, okay, prevents it. You push on the floor pushes back, you feel like you have weight. You don't, but you feel like it because it's using your inertia to produce a force that feels like gravity, okay? Same idea. Everybody all right with that? Now, as you go around this corner, you want to rely on static friction because static friction is always greater than kinetic friction, right? So cornering, you want to not slide. If you start to slide, you're going to rely on kinetic friction, which will usually result in you going places you don't want to go. All right, so we want to have static friction. Okay, so we're going around this corner, okay, using static friction, the car's tires are not sliding. So what if I want to drift the corner? Not that we would do that because that usually results in you hitting poles. I'm sorry, I couldn't resist. Okay. So if I'm drifting this corner, but I'm actually good at it, okay, and I don't hit a pole, am I relying on static friction or am I relying on kinetic friction? If you're drifting, are your tires spinning? Okay, so there is a bit of kinetic friction involved there, but the difference is, you have to have rear wheel drive, by the way, for this to really work well, okay, is you're going to tilt the car. So you're going to angle the car so it's pointed a little bit towards the center. And then as the tires spin, they produce a pushing force that acts towards the center of the circle. A component of it anyway, because you're sliding and spinning the tires, okay? You're basically changing the forces that are pushing you towards the center of the circle, all right? Now, how many people think that you could drift a course faster than you could just go around it without drifting? Okay? Like we see racing and it makes it look like drifting should be better, right? Like it should be faster, except it never is, okay? You would never see a Formula One driver drift corners in a race because it isn't faster. It's faster to rely on static friction. Now, if you're watching a drifting race, that's totally different. Those guys just drift because it's a drifting race, okay? But there was actually an episode of the Mythbusters way back, and they brought in the Drift King guy, okay, from Japan, okay? And they had him drive a course that they had set up and drift every corner, and then both Adam and Jamie drove the same course in the same car and didn't drift the corners, and they were faster than a professional drift racer, okay? Drifting is going to mean a couple of things. As I go around the corner, I might actually be able to take the corner a little bit faster if I'm really good. But the problem is, when I get around the corner, what are my tires doing? They're spinning. How well does that propel me forward when I'm done the corner? Does it propel me forward as well as if my tires aren't spinning? That's the flaw. Okay? A person who drives around this corner using static friction is going to be able to do it at almost the same speed as a person who drifts it. The difference is when they complete the corner, they can engage the full force of their engine because their tires aren't spinning. Okay? And they can get more force because they're using static friction than the person who's drifting and their tires are already spinning. Okay? That's kind of the strength of it. Okay, everybody okay with the idea of going around that corner? Okay, so I'm relying on friction because this corner is flat. Okay, it's what we call an unbanked corner. All right, so the challenge in this part of the unit is figuring out what force is acting as a centripetal force. Okay, in a cornering test, okay, and this is something that all automakers do, okay, they'll have a skid pad test. Okay, and what they do is they have an area of the track that's just a big flat area with a circle painted on it. Okay? Their test driver gets in the car and just drives around that circle at ever increasing speeds until the car skids out. Okay? And from that top speed and knowing the radius of the corner, they can calculate the cornering ability of the car. Okay? It's usually measured as a G-force. Most passenger sedan kind of vehicles can corner around 0.7 to 0.8 Gs. Okay? That means if you were the passenger, okay, you would be pressed up against the window and the window would push back with 0.8 Gs. So 80% of your weight against your face. All right? A really high-end sports car could possibly go over 1 G. Okay, so if you had a really high-end sports car on that cornering test, you might be able to go more than 1 G. Now that means for the driver, you gotta hold on tight because you're trying to hold on to the wheel, but your body wants you to go the other way or into the window, depending on which way you're going. Okay, you have to hold on to that wheel while your whole weight is trying to go the other way and take you away. All right, so there's a lot of kind of G-force involved in that if you have a high-end vehicle. Now, if you drive something tall, okay, like a truck or an SUV or a cargo van, okay, you don't take corners very fast because you might what? You might tip over, okay? If you drive an SUV, pull down your sun shield. Usually on the back is a warning about how you might tip over if you go too fast. Okay? The reason for that is something low to the ground, most of its mass is close to the ground. Okay? If you're in something taller, okay, your center of mass is a lot higher above the ground than this car's is, which means your inertia is higher. Your moment of inertia is higher, which can lead to you rolling over. Okay? There's a rotational aspect to your inertia. All right? It's why you never see, a live in the van life van, okay, winning a cornering contest against a Corvette. Okay? It's just too tall. Right? Everybody okay with that idea? Right. So here's what we're going to do. We are going to calculate, okay, the maximum speed for this car to safely negotiate an unbanked corner with a radius of 50 meters in dry weather, where our coefficient of friction is 0.9, and icy weather, where our coefficient of friction is 0.1. Okay, so 9 times less friction available in the icy conditions. Prediction: if I have 9 times less friction, how much slower am I going to have to go? Okay, remember, we're working backwards this time. 3 times slower. I have 9 times less force. Okay, if I'm working backwards, I would have to go 3 times slower, right? Because of that exponential relationship. Okay, let's see if it works out that way. So here's what we do. We figure out first what's providing the centripetal force. This is kind of the vector sum of all forces part of a centripetal force problem. My centripetal force, or net force, is being provided by the force of friction if I'm on an unbanked corner. That's all there is to push me back towards the middle. Okay, I'll show you an example where somebody figured out a smarter way. Okay, it's brilliant, and it actually resulted in a rule change in racing. Okay. So you've got your centripetal force being provided by the force of friction, so those two are equal. Okay, the way we calculate centripetal force: mass times centripetal acceleration, mv squared over r. For the force of friction, mu times normal force. Since the ground is level, normal force would be equal to what force? Gravity, right? Right now, I'm standing on a level floor. The normal force and gravity are equal. Same is true here. All right, so I'm going to have mv squared over r equals mu times m times g. What's going to happen to the m? It's going to cancel. Okay? Now, this is a perfect physical world situation. It actually doesn't matter in a perfect physical world what the mass is. You could go the same speed. Now, we understand that in the real world, more mass usually means the moment of mass or moment of inertia or center of gravity, whatever you want to call it, is higher, and that can cause a rotation. Okay? So, mass is going to cancel, okay? And we're looking for v. So, I'm going to multiply both sides by r. So, r is going to come over here. Okay? I have v squared equals mu times g times r. So, to calculate v would mean the square root of mu. mu times g times r, mu-gar. Okay? So, now I've got my formula, all I have to do are plug in my numbers. So let's do the dry weather, the ideal situation first. Okay? So V will equal the square root of 0.9 mu times 9.81 times the radius, 50 meters. Okay, so under ideal conditions, that car should be able to take that corner at 21 meters per second. Okay, under ideal dry road conditions. Okay. In the icy conditions, we have 9 times less friction available, 0.1 instead of 0.9, times 9.81 times 50. Okay, so I'm going to get a number here 9 times smaller, but the square root of 9 is 3. Okay, so instead of 21, this should come out to 7. Okay. Okay, 7 meters per second. So we kind of have to remember that the next time we encounter slippery roads. Okay, you are going to have to go a lot slower. Okay, if the speed limit is 40, you don't go 30, you go 15 or 10, okay, around that corner, okay, to ensure that you have enough friction available to keep you in the corner. Because that is exactly what happened to the dude who ended up in the pond. Okay, he should have been going 10 and he was easily going 40. Okay, which is not a good speed to take that corner at, even in good conditions. Okay, but that's how fast he was going. Okay? I have no idea how fast the guy who hit the pole was going. Too fast would be my first thought. Okay, but I don't know what his actual number was, but he did a job on that pole. And that pole had a concrete piling that went down pretty far into the ground. Okay, too fast would be my first thought. Okay, does that make sense? Okay, so here's what we have to remember. For an unbanked corner, friction provides the centripetal force. Okay, unbanked corners are a question type that is going to come up all the time. In an unbanked corner, friction provides the centripetal force. Okay, so that was childish. So I'm going to show you now a professional NASCAR racer who figured out a loophole to this physics problem. Okay, he needed to finish, I think, 4th in this particular race in order to qualify for the championship race. He was in 9th or 10th. Okay, and it would be pretty hard to make up that much ground in one lap. Okay, especially knowing that you could only rely on the bank of the corner and the force of friction to keep you in the corner. So he cheated. Well, it's cheating now. It wasn't cheating when he did it. It was a dirty play when he did it, but it wasn't cheating technically when he did it. It was actually really, really smart. On a track, you can have the force of the bank, okay, which we're going to talk about in a little bit, and the force of friction. And that's it. Unless you do something no one would think to do. What did he do? Yeah. He ran his car into the wall and floored it. When he pushes on the wall, what does the wall do? Pushes back. Now he had to do this only on the last lap because it destroyed his car. Okay? It like ruined the tires, it destroyed the bodywork on that whole side, but it was the last lap. All he had to do was move from 9th or 10th to 4th. Okay? They've since outlawed this maneuver, okay, because obviously everybody would do it if it was on the last lap, and it's not super safe either. Okay, but I'll show you kind of what that looked like here. Thank you. All right, so that's the math we just did, okay? Big thing here, if you're on an unbanked corner, you're strictly relying on friction to allow you to turn, okay? So we simply set centripetal force equal to the force of friction, okay? So that's gonna be mv squared over r equals mu times m times g. We manipulate and solve, and then we plug in our numbers. Okay, so just like what we did, we got 21 meters per second, okay, for the 0.9, and we got 7 meters per second for the 0.1 of that. Yeah. Wait, good enough. Yeah. Okay, everybody all right with that idea? All right. Now, obviously, conditions, road conditions, dictate how much friction is available. All right. Especially in Canada, because conditions can change so rapidly and so severely. We want to be able to provide other forces that are more reliable to make driving safer. Okay? One of the best ways to do that is to bank the corner. Okay? Now, when you go around a banked corner, just like those racers did, you are still relying on friction to an extent. But there is a guaranteed safe speed for any banked corner where you wouldn't rely on friction at all. The delicate balance here is if it's that slippery, if you're a little bit too fast, you'll slide out. And if you're a little bit too slow, you slide in. Okay? And I've actually seen this happen. Okay? Back before they did the whole Stony interchange there on McLeod, okay? There just used to be 22X in McLeod. Okay? And coming off of 22X, there was a little on-ramp. Okay? It was a pretty tight corner, actually. It was pretty steeply banked because it was so tight. And I came up on that, and it was a day where there was freezing rain. Okay, I was coming up at it, and I knew that the speed limit on that corner was 40. Okay, I came into the corner at 40. The problem was the person in front of me was being overly cautious, and they were going a lot less than 40. Okay, and being a physics person, I'm like, oh no, I'm going to have to slow down, and if I slow down, I'm going to slide into the middle of this corner, to the marsh that's in the middle. Okay, so as they rounded the corner, I could see them starting to go. Okay, so I was still going about 35, 38. There was enough traction that I was able to increase my speed. I actually dropped a little bit, okay, but I got to a radius where that was okay, and I watched them slide right in, and I went all the way around the corner because I knew it was so slippery. I had to go exactly what the corner said to go. Okay? It was almost like perfectly frictionless conditions, if you can imagine that. Okay? And I took that corner at just the right speed to stay in it. Okay? If you go a little bit faster than that, you're in the guardrail. Okay? You go a little bit slower, like the person in front of me, and you slide in because it's an inclined plane. Basically, all we're doing with a banked corner is taking an inclined plane and making it a circle. Okay? When you push on an inclined plane, what does the inclined plane do? Pushes back. Okay, so just like what we learned in Unit 2. Okay, if I've got an inclined plane and my car is on it, okay, gravity pulls down, normal force pushes straight out. Now, does that normal force have both a vertical and a horizontal component? It does. Okay, the horizontal component, okay, is going to point towards the center. If this is a corner and it's wrapped around like this, okay, that horizontal component is going to point back towards the center. Okay, right here it's pointing back. Over here it's not. Okay, so it's pointing right back towards the center. Is that providing some centripetal force? If it points towards the center, it does. Okay, not a lot, but it's enough. Okay, to guarantee a safe speed. You would also have friction, okay, on an inclined plane. Okay, friction, if you're trying to go that way, friction would act into the middle, and it would also have, it would act down the plane, it would also have a coefficient of friction that points, or sorry, a component of friction that points back in. Okay, everybody with me there? All right, now, that's if I'm just sitting on the corner. If I'm driving around the corner, does my inertia push on the ground harder than if I'm just sitting there? right? If I'm going around this corner, okay, my inertia wants me to go straight. The surface of the corner prevents me from doing that. So I push on the corner and the corner pushes back, but more than if I was just sitting on the corner. Okay, so what we get is a kind of a reversed situation. Okay, so now it's a corner, and now normal force is the bigger force, because it's not just gravity. There's also my inertia pushing on the corner. Okay, so normal force becomes the big side. Okay, this side here would be gravity, and now it's smaller. Okay, and this side would be my centripetal force, because it would point back towards the middle. Okay, so banking the ground makes it easier to take the corner, because you get additional force. You not only have friction, but you also have the component of your normal force helping you back towards the middle. Okay? That is all based on how fast you're going, because the faster you're going, the harder you'll push on the corner, and the angle they bank the corner at. Okay? The bigger the angle, the more you're going to push. Now, the more the angle, the more likely you also are to slide down. Okay? That's why they don't bank exit ramps like they bank racetracks. Okay? Racetracks are like really steep. In fact, so steep that when they pave them, they have to use a crane to hold the paving machine on so it doesn't slide down. Okay? So the steeper it's banked, the faster you have to go to stay on. Okay? How many people have ever watched the indoor cycling at the Olympics? Okay? It's almost like this. It's almost straight up and down, and the bikes are traveling around and around like this. It's almost like the Gravitron at the Stampede. Anyone ever ride that? Callaway Park also has kind of one like that, right? Where you spin around and around, and then the floor drops away and you're pinned to the wall and you can't fall. Okay? If you really know what you're doing, you can stand on the wall, okay, and you won't fall. Right? Same idea. It's just spinning fast enough that you push on the wall, and the wall pushes back harder than gravity's trying to pull you down. Okay? So it feels like there's no gravity. Okay? Same is true here. So a couple of things to influence how fast you can take that corner. Okay? The angle of bank and the radius of the corner, and of course gravity. Okay? But that's going to be kind of a fixed number for us, since as far as we know, banked curves only exist on Earth. We haven't proven otherwise. Okay, so let's look at a banked curve here. Okay, so as we were saying, roadway friction varies. Okay, it could rain, it could snow, it could be perfect. Okay, but the amount of friction available on a banked corner is going to change. So banked corners are designed to give you a guaranteed safe speed regardless of the road conditions. Okay, so that one out here, I think is it 60? It's terrible that I don't know what that is. Probably means I take it too fast on a regular basis. Okay, I think it's 60. We'll just say that it's 60. Okay, no matter how slippery that corner is, if you take it at whatever the posted speed limit is, you're safe. You won't slide out. Don't go slower, just slide in. Okay, now on a nice day, no, you don't have to worry about sliding in either. You could go slower, you just have to worry about the guy's going to run into the back of you who's going 60. Okay. So you take that corner, there's a guaranteed speed, and that guaranteed speed is based on how big is the corner, the radius of the corner, and how much is it banked. Okay, how steep is it? That one's fairly steep. It's probably about 8 or 9 degrees. I know that doesn't seem like a lot, but that's actually pretty steep. Okay, you don't want to bank it too much, because then when it's slippery, people could slide into it. Okay? And there's that whole, if I'm going around at the right speed and I have coffee without a lid, I don't have to worry about it spilling. But if I go too fast, is it possible the coffee could come out of my cup and spill everywhere? Okay? That's that other thing. Okay? So, all right. So what we've got here is you bank the corner, you're using other forces. Planes do the same thing. Okay? If a plane wants to turn, it can't just turn the rudder. I mean, that'll make small course corrections. It's not going to make a big turn by just turning the tail rudder like this. Okay? What it does instead is banks the wings. Then it's using the lift the wings produce to push back towards the middle. Okay, how many people have ever been on a plane before? right? And you can feel, like when the plane wants to make a big turn, you can feel the plane go like this. They bank in order to turn, right? What that does is two things. It allows them to lose altitude slowly and make turns, make course corrections. So usually planes do it when they're approaching or on approach to land. Okay, so they'll make a couple of turns to help them drop altitude, okay, and kind of get down and get on course for where they need to go. So here's how that works. If the plane wants to fly straight and level, the wings have to produce a force upwards that is equal to gravity. So the net force is zero and they stay flying straight and level. That's what wings do. That shape of the wing produces lift. Okay? The air that goes under the wing and the air that goes over the top of the wing travel at different speeds, and that produces a force that lifts the plane. Okay? When you bank the plane, that lifting force is always perpendicular to the wings. So as soon as the plane banks, some of that force is directed laterally. Okay? So you would have this horizontal part of that lifting force that would act back towards the center. But now, the vertical component of it, which is supposed to offset gravity, isn't as big. So if it's not as big as gravity, the plane falls. I mean, not falls, but like descends slowly, accelerates downwards a little bit. Okay? Because now the wing's lift isn't entirely vertical. What if the plane stood on its side? Is it going to turn fast? What else is it going to do? Fall, like at 9.81 meters per second squared, because now the wings are not producing any vertical force. All of their force is horizontal. It's why in movies like Top Gun, okay, you would actually see them, they would bank if they were being attacked, right? They always say bank right or bank left. Okay? The reason for doing that is it makes you move in 2 dimensions and it's harder to track you. So if you bank like this and stand your plane on its side, you don't just turn hard in one direction, you fall as well, okay? Making it harder for them to hit you because you're moving now in 2 dimensions. It's why it's a tactic that's often used that way. Okay, does that sort of make sense? Okay? So when you bank a plane, it's the same as banking a corner. You're just changing the vector of the forces that are available in order to help you turn better. Okay, so this is what I was trying to draw earlier. I should have just shown the picture because my drawing is terrible. Okay, so when you go around a banked corner, what you're really doing is staying on an inclined plane. But because your inertia wants you to go this way, you push on the corner, and the corner pushes back. But normal force, just like lift, can only push perpendicular to the surface. Okay? So yes, I push on the corner, and the corner pushes back, and that increases the force it exerts on the tires of my car. Okay? And that means that there would be a horizontal component and a vertical component. Okay? That vertical component is going to offset gravity, and I won't fall through the ramp corner. Okay? All right, so that's what we've got here. Okay? And they draw this is why I don't like this diagram. They draw that horizontal force down here when it should really be up here. Okay? So there's the angle. It's the same angle as here. Okay? So what we're really looking at is that this normal force is the hypotenuse of the triangle. Okay? Everybody all right with that? Okay. So if I wanted to find this angle, and I know how to calculate this force because it would be Fc, and I know how to calculate this force because it would be Fg, okay, could I use trigonometry to figure out my angle? Okay, so I know the opposite side and I know the adjacent side. Agreed? What's opposite over adjacent? Tan. All right, so the tan of theta is going to be the opposite side over the adjacent side. Okay, now, what's going to happen to the ends? Jordan? They're going to cancel. Does that sort of make sense when you think back to the last time you were on an exit ramp? How many speed limits were there? 1. Because the bank affects all objects equally regardless of their mass. Can you imagine if mass was a factor? There would have to be 1,000 different signs on every bank curve. If you weigh this much, you have to go this speed. If you have a mass of this much, you have to go this speed. They would be completely useless, right? So the angle of bank affects all vehicles equally, okay? Because it just has to do with their inertia, okay? So mass will cancel, and what I'm really left with here is this. The tan of theta equals v squared over r times g. Mass is irrelevant for a banked corner, and it was also irrelevant for an unbanked corner. Okay, which is good because all vehicles should negotiate corners in the same way. All right, that formula there is on your formula sheet. You'll never be asked to do what I just did. Okay, you will never be asked to derive that formula. That's what I just did. Shows you how I got it and where it came from. That formula is on your formula sheet. That formula is the banked curve formula. So when a city planner, okay, goes about designing an interchange, they're going to use that formula. Okay, they're going to know how much room they have. That would be the radius of the corner. Okay, and they're going to have a speed in mind for how fast they want people to take that corner. Usually between 30 and 60 kilometers per hour. Okay? From there, they pick a speed and they say, bank it this much. All right? That's how those kinds of things are designed. It's actually a pretty simple formula. Okay? But it's important for designing safe roadways. And if you make that too steep, people are sliding into it all the time. If you don't make it steep enough, people are sliding out of it all the time and hitting the guardrail. Okay? Everybody with me there? Okay. All right, so that's your bank curve formula. Know that one. You are going to get questions on bank and unbanked curves.
Cool.
Yeah, did you get to go read?
Yeah.
All right, making sense? Okay, so friction holds you in an unbanked curve. Normal force, based on the angle of bank, holds you in a banked curve. Okay, really important to remember those two things so that you can tell the difference between the two types of questions on a unit exam. Okay, we're going to go over a few examples of each one here now. Okay, so in the real world, we just did this imagining that the curve was frictionless. I mean, that basically never happens. Okay, in the real world, you would also have the force of friction helping you on a bank corner. Okay, so the force of friction is mu times the normal force, but remember, your car is wanting to go this way. Okay, so force of friction actually acts downwards and also has a horizontal component that helps keep you in the corner. The problem is that's not a force that's always the same number. That's the force that can vary depending on road conditions. Okay, so that big on-ramp out there, okay, if the speed limit is 60, under perfect conditions, could you go faster than that? I'm not saying you should. I'm asking, could you? Okay, and the answer is yes. Okay, in fact, that's usually why exit ramps have yellow speed signs and not white. Okay, white sign means that's the maximum limit. That's how fast you can go. Go faster than that, you get a ticket. The signs in yellow, it's a recommended speed. Okay, you could take that corner faster than that, but we don't recommend it. Okay, so if the conditions are perfect, it's not covered in little rocks like it is in the wintertime, okay, or ice, okay, or it's not wet, then you could probably go faster than that. Okay, but that is the guaranteed safe speed. All right. So let's kind of ignore my work here and just say, we want to figure out the angle at which a frictionless curve should be banked for a speed of 35 meters per second and a radius of 550 meters. This is a very big curve. Okay, it has a radius of over half a kilometer. All right, so we're going to use this formula here, okay, tan of theta equals v squared over r times g, and we're just looking for theta. Okay, so to solve for theta, we're just going to move tan over to the other side. So that'll mean inverse tan times v squared over r times g. So inverse tan of 35 squared. This is clearly a racing corner because 35 meters per second is like 130. Okay, don't take that corner at 130. Okay, that's not safe. Okay, divided by the radius, 550 times 9.81. All right, if we punch that in. Okay, so second 10 of 35 squared divided by 550 times 9.81. All right, should be banked at 13 degrees. Okay, that's, believe it or not, doesn't sound like a lot, but 13 degrees is pretty steep. Okay, for a banked curve. Okay, everybody all right with how that works? Okay, so in a question like that, I could give you the angle and ask you to calculate the speed, or I could give the angle and the speed and ask you to calculate the radius. Okay, there's really only a few ways a question like that can go. Okay, that's part of why this is one of the easier units. Okay, for basically every question type, there's not a lot of ways I can change it to make it tricky. Okay, we basically just set up one way. Okay, we're not going to do this one, we're going to talk about this example. Okay, how many people have ever got a rock in their windshield? Okay, it's annoying. All right, why does that happen? Like, where does that rock come from? The tire of the person in front of you. Okay, now, you're most likely to get a rock in the windshield when the car in front of you is accelerating. And by accelerating, I mean speeding up. Okay, so the rock gets embedded in the tread of the tire, so stuck in between a couple of pieces of the tread pattern, right? So stuck in between some rubber. What's keeping the rock there is friction, okay? Friction between the rock and the pieces of the tire it's stuck between, all right? At low speeds, that force of friction is probably enough to keep it in the tire. Okay? But as the tire turns faster and faster, the inertia of the rock will overcome the friction holding it in. And at that point, it will be ejected. All right? Now, it's also most likely to be ejected where? Where do you think that rock is most likely to lose its friction and be ejected? Like what point in the circle? I mean, if it gets lost here, it's going to go that way. You don't have to worry about that. You're going to hear that inside the fender well. That happens sometimes. Okay? So where is it most likely to lose enough friction and be ejected and end up in your windshield? That's the trajectory that will hit your windshield. The reason it's going to be ejected at the bottom is because when your tire is in contact with the road, that part of the tire flattens because the weight of your car is pushing down on it, right? Okay, so the bottom of your tire is always a little bit different shape than the rest of the circle because it's being pushed. That opens the tread. Okay, when the tire gets squished, the tread opens. That's where the rock is most likely to lose and be ejected. And that ejection is going to make a projectile arc that is going to encounter your windshield. Okay? So, if the person in front of you is speeding up, that's when it can happen. Okay? Because they're changing the speed at which the tire is rotating and making it more likely the rock will be ejected. Okay? It could also happen on a lane change because you've got some lateral motion there that can also open up. Okay? So they could be traveling at a constant speed, but they change lanes in front of you and throw a rock at you. Okay? Anything that can make that tire change shape is when it's going to be ejected. If they're just traveling at a constant speed in front of you, it's probably not going to happen. Okay? The forces are all pretty constant and nothing's really going to change. Okay? Unless the rock breaks. That can sometimes happen, right? The weight of the car just happens to wear the rock down enough. Okay? Has anyone ever seen what a rock looks like if it's been in your tire for a long time? Okay? It's flat. It gets worn. Okay? It's smooth and flat in the same shape as your tire if it's been stuck in there for a long time. Okay. Everybody all right with that idea? Okay, so there you go. Now you might avoid some costly windshield repairs / replacements. Okay? If you know that that's when it can be ejected, you know that that's when you should back off a little bit. Okay, I want you guys to try question number 2. It's more about what we did yesterday. So it's more about these formulas here. Or that formula there, I should say. Okay? Give that one a try. We'll end off with that one. That for this one, the other way to write that formula is 2 pi r times the frequency, because we were given the frequency in that question, right? It said 716 hertz. Okay? Imagine a star that spins around completely in 716 times per second. Okay? Pulsars are weird things. Okay? So here's what we know for that question. We know the radius is 16,100 meters, because we have to have it in meters. Okay? We know the frequency is 716 hertz. Okay? V is 2 pi r times f. So 2 times pi times 16,100 meters times 716 hertz. Okay? That means that star is spinning at 7.24 times 10 to the 7 meters per second. To give you reference, that is the speed of light. Is that pulsar spinning really fast? Okay, like you would feel relativistic effects there. Okay, time would pass more slowly for you than others. Okay, it would be a big deal. Okay, all right, we'll leave it there for today, guys.
Yeah, no, but you talked to